Right, we're going to take a look at another method for solving a system of equations using matrices, and that's using the inverse matrix method for solving a system of equations. So I'll show you how to do it by hand, and we also did an example using the TI-83, or you can use an 84 or 89 or TI-Inspire to do the same thing. So first we got to make sure that our matrix is invertible, meaning we have some sort of solution. So let's say we have a matrix equation AX equals B, and so think of it like if you're just solving an equation. If we were solving for X, X is attached by a multiple. A and X are attached by multiplication, so we divide both sides by A. Well, we don't really have a matrix division. It's kind of a different operation. We do have an inverse, though. So if I multiply something by its inverse, for example, if I multiply 2 inverse times 2, 2 inverse is just 1/2 times 2, which is 1, and 1 is what's called a multiplicative identity, just meaning if I multiply anything by 1, it doesn't change anything. Some matrices, not everything has a inverse. Just like 0 doesn't have an inverse for multiplication. No matter what I multiply 0 by, I'm always going to get 0. I'm never going to get to 1. So let's say we have this matrix equation AX equals B, and we do have an inverse. We'll call it A inverse. And matrix multiplication is generally not commutative, which means I can't multiply on either side. So an example is, for instance, 2 times 3 is the same thing as 3 times 2 with just a regular arithmetic. But with matrix arithmetic, it's not quite the same. Sometimes the dimensions won't even match up for us to multiply the matrices. So we're going to multiply on the left-hand side. And just like with 2 to the minus 1 times 2, I'm going to be left with the identity. We call it I, and then times X, and that's equal to A inverse B. And when I multiply something by the identity, it doesn't change anything, so X is equal to A inverse B. So when you're trying to solve a system of equations by inverse method, all it really amounts to is, can I get the inverse matrix? And then I'm going to multiply it by the coefficient matrix B, and we'll talk about what that is in just a moment here. Okay. So I'm just going to do an example of how we represent a system of equations a little bit of a different way, not as an augmented matrix, but as a system of equations, or as a matrix equation. So we'll take our coefficient matrix, which is just the coefficients on the variables, and then we'll have a vector of x and y, and then that'll be equal to the coefficient. That's our b. So this would be our a, this would be our x, and this would be your b. You can use an uppercase or lowercase b, doesn't really matter. Okay. Now if I do the matrix multiplication, it's row times column. So we'll do 3 and the negative 1 times the x and the y, so that gives me 3x and a negative y. And then I'll do negative 2 times x and 1 times y. Okay. And I have a 2 by 1 equals a 2 by 1. So I do have the same thing. So I have 3x minus y equals 8. 2x plus y equals 4. So it's just another way of representing a system of equations. Okay? Alright. So I'm going to do an example of how do I find the inverse by hand. In class, probably due to our time constraints this semester, we learned how to do this in the 83 or the 84, or you learned how to do it in your TI-89. But if we want to do it by hand, what I do is I take the coefficient matrix and I augment it with the identity, and on this other side, or the left side of the matrix, I'm going for this. I'm going to do the Gauss-Jordan on the no, that's one, yeah. I'm going to do Gauss-Jordan on the left side of the matrix, and whatever happens to the right happens to the right, and the right matrix when we're all done is going to be identity matrix. Okay, so we may get some fractions here, so I want to make this 3 into a 1. So I'm going to multiply by the reciprocal, which is 1/3. So 1/3 row 1 replaces row 1. So we get 1, negative 1/3, 1/3, and 0. And the bottom row is unaffected. Now I would like to make a 0 there. To make a 0 in column 1, we're going to use row 1, and the opposite of negative 2 is 2. So 2 row 1 plus row 2 is going to replace row 2. Okay, so I'll write it out this time. And I don't know if I'll write it out every time, but that's what's going on. So our new row 2 becomes 0, 1/3, 2/3, and 1. So row 1 is unaffected. Row 2 becomes 0, 1/3, 2/3, and 1. Okay. Now I'd like to make this a 1. To make a 1, we're going to multiply it by the reciprocal. The reciprocal of 1/3 is 3. So we're going to do 3 row 2 to replace row 2. Top row is unaffected. 3 times 0 is 0, 3 times 1/3 is 1, 3 times 2/3 is 2, and 3 times 1 is 3. Okay, so we're almost done. All I want to do now is make this a 0. To make a 0 in column 2, I'm going to use row 2, and we're going to use the opposite of negative 1/3, which is positive 1/3. So 1/3 row 2 added to row 1 is going to replace row 1. Bottom row is unaffected. The top row, 0 times 1/3 is 0, added to 1 is 1. 1/3 times 1 is 1/3, added to the negative 1/3 is 0. Okay. 1/3 times 2 is 2/3, added to 1/3 is 3/3, which is a whole. And then finally, 3 times 1/3 is 1, added to 0 is 1/3. This right here, the 1, 1, 2, 3, that is now my inverse matrix. That is A inverse. Okay. On the next slide, I'm going to show you if I multiply A inverse times A, I'm going to get the identity matrix. You can also multiply on the right-hand side. It'll work the same way. Inverses are unique. Okay. So we're going to do row 1 times column 1, so we're making sure we got 2 by 2, rows match columns. Okay, so we'll do that matrix multiplication, rows times columns. Alright, and we certainly get the identity for 2 by 2, so identity 2 by 2 matrix, which is good. Okay, so when I solve AX equals B by the inverse method, all I got to remember is I'm going to multiply A inverse times the constant part, whatever your system of equations, the two things it's equal to. Okay, or three things depending on how big the matrix is. All right, so A inverse B for this particular one was 1, 1, 2, 3, and then our B was 8, 4 for this particular example we've been playing with. Okay, so it's a 2 by 2 times a 2 by 1, so columns match rows, so we're good, and we're going to be left with a 2 by 1 matrix when we're all done. So we're going to do 1 times 8 and 1 times 4, so 8 plus 4 is 12 for the top entry. And then we'll do 2 times 8, which is 16, 3 times 4 is 12, 16 plus 12 is, I believe, 28. Okay, so my solution is 12 and 28, and that's my solution using the inverse method. Again, try to have fun. Your outlook plays big role on how things go with this. Okay, let's do one more where I give you the inverse matrix, and you just got to remember it's A inverse B. So let's say given that A inverse is equal to, I think it's a bunch of halves, a half, negative 1/2, a half, and a half. And I would like to solve x minus y equals 6, x plus y equals 4. Now if I wanted to, I could go ahead and do this to find that if I wanted to find that inverse matrix, eventually it's going to become that if I do the Gaussian elimination. It'll take a little bit of time. We saw how to get that with technology in class. Okay. Oftentimes I might just give you the inverse and say solve by inverse method on the test or the final. Okay, so and we say using the inverse method. Now this looks super easy to do by elimination method, but we want to expose ourselves to other methods, and this is a nice basic example. So x is going to equal a inverse b. So a inverse is a half. Don't let those fractions scare you. It's going to be a nice problem. Okay, and our b is 6 and 4. Alright, so multiplying by halves, and we're left with 5 and -1, and that is our solution using the inverse method. So this can be a very straightforward, very quick problem. You may see something like this on your final. Given this is the inverse, find the solution to this system of equations. Okay?